Dear students, today we are going to discuss about 12th lesson topic electrostatics. Electrostatics is a branch of physics which deals with about static electric charges. Mainly we are going to focus important topic in electrostatic lesson. First, Coulomb's inverse square law in electrostatics. Coulomb was studied force between two charged bodies. According to Coulomb's law, let us consider two point charges. Q1 is one of the point charge, Q2 is the another point charge. These two point charges is situated in air or vacuum or free space. The distance of separation between the two point charges are apart in air medium. According to Coulomb's law, this Q1 charge repels the Q2 charge with the repulsive force F. Simultaneously, this Q2 charge exerted repulsive force on Q1 charge with the repulsive force F. According to Coulomb's law, the force of attraction or repulsion between the two point charge is directly proportional to product of the two point charges. Then, force of attraction or repulsion between the two point charges is inversely proportional to square of the distance between them. Equation number 1, equation number 2. Both the equation combined together, force of attraction or repulsion between the two point charges is proportional to Q1, Q2 divided by R square. F. Remove the proportionality, put the equal. We are introducing one constant. That constant is K. Q1, Q2 divided by R square, where K is the proportionality constant. So, from this equation, we are going to calculate the force of attraction or repulsion between the two point charges. According to Coulomb's law, F is equal to K, Q1, Q2 divided by R square. See, here expression to represents the proportionality constant F into R square divided by Q1, Q2, which is equal to K. Here K is equal to 1 divided by 4 pi epsilon naught. That value 9 into 10 power 9. Unit of K value Newton meter square divided by Coulomb square, or Newton meter square Coulomb power minus 2. It is a SI unit of proportionality constant K. The expression to represents the proportionality constant 1 divided by 4 pi epsilon naught. Value of proportionality constant 9 into 10 power 9 Newton meter square Coulomb power minus 2. So, force of attraction or repulsion between the two point charges can be calculated with the help of Coulomb's law. F is equal to K Q1 Q2 divided by R square. Then the force of repulsion or attraction between the two point charges is acting along the line joining between the two charges. Here Q1 charge and the Q2 charge, both the charges similar charge. Q1 charge exerted repulsive force acting along the line joining between the two charges. Q2 charge exerted repulsive force on Q1 charge is acting along the line joining between the two charges. Then these two charges is situated in a medium without any disturbing. That entire system is situated within a medium, that medium of permittivity epsilon, that medium of relative permittivity epsilon naught. That entire system is situated within a medium Q1, Q2, distance of same separation apart. That force of repulsion between the two point charges in a medium F1, which is equal to 1 divided by 4 pi epsilon Q1, Q2 divided by R square. So therefore, epsilon, which is equal to epsilon naught, substitute here force between the two charges, point charges inside the medium 1 divided by 4 pi epsilon naught Q1, Q2 divided by R square. Then F1, which is equal to 1 divided by 4 pi epsilon naught Q1, Q2 divided by R square is force between the two point charges in R medium. So therefore, force between the two point charges in medium F1, which is equal to F divided by epsilon naught. Then force between the two point charges inside the medium is decreases epsilon naught times. Then F1 divided by F, which is equal to 1 divided by epsilon r. Take the reciprocal, force between the 2 point charges in air medium divided by force between the 2 point charges in the medium, which is equal to epsilon r. Unit of relative permittivity of medium. Expression to represents relative permittivity of medium. Epsilon r is equal to force between the 2 point charges in air medium divided by force between the 2 point charges in medium. Newton divided by Newton, they cancel with each other. Another expression to represents epsilon r, epsilon which is equal to epsilon naught epsilon r, epsilon r is equal to epsilon divided by epsilon r. So both permittivity of medium divided by relative permittivity of R medium, both as the same unit, get cancelled with each other. Relative permittivity of medium, there is no unit. So next topic, electric field intensity. Let us consider one point charge Q is situated in R medium. It will produce electric field around it. We don't know electric field is established by a source charge, but we are going to calculate the electric field produced by the source charge. Then let us consider one test charge Q0. Then the test charge is placed within the region around the source charge. The test charge experiences electric force. Then we are going to calculate, yes, electric field is produced by the source charge. Then electric field intensity. Electric field intensity notation E, which is equal to electric force experienced per unit test charge kept at that point, is called electric field intensity. Electric field intensity SI unit, electric force Newton, charge Coulomb, Newton Coulomb inverse. So very important definition. Electric field intensity is defined as electric force experienced per unit positive test charge kept in an electric field is called electric field intensity. Electric field intensity is a vector quantity E vector, which is equal to F vector divided by Q naught. So electric force experienced per unit test charge kept at that point, F is equal to E Q naught. So magnitude of electric force experienced by a charge subjected within electric field, modulus of F vector is equal to modulus of E vector into Q naught. Then electric dipole. So what is electric dipole? There are two equal charge Q, Q, and dissimilar charge minus Q and plus Q separated by a 2D distance. It will constitute electric dipole. So electric dipole is defined as two equal and dissimilar charges separated by a very short distance. It will constitute electric dipole. Electric dipole has a permanent electric dipole moment. Electric dipole moment acts from minus Q charge to plus Q charge. Electric dipole moment is a vector quantity. Direction of electric dipole moment acts from minus Q charge to plus Q charge. What is electric dipole moment? Magnitude of electric dipole moment is defined as the product of magnitude of any one of the charge and the dipole distance 2D. So electric dipole moment is a vector quantity P vector, which is equal to Q into 2D vector. So electric dipole moment is a vector quantity, both is as magnitude and direction. SI unit of dipole moment. SI unit of dipole moment is SI unit of charge Coulomb. Dipole distance is measured in meter. So it is a SI unit of dipole moment Coulomb meter. So next topic, electric field due to dipole at a point on its axial line. Let us consider one dipole minus Q charge plus Q charge, two equal magnitude and dissimilar charges separated by a 2D distance. It will constitute electric dipole. Midpoint of the electric dipole O. Direction of dipole moment acts from minus Q charge to plus Q charge. Let us consider one point on its axial line of electric dipole. Point P. distance of the point to P from its midpoint of the electric dipole is R. So, plus Q point charge produces electric field at this point to P, direction away E1. Negative charge produces electric field at this point to P, directed towards the negative charge E2. So, both the charges in electric dipole produces electric field intensity at a point P on its axial line of electric dipole. So, resultant electric field at this point to P is E is equal to 2P. So, electric field at a point on its axial line of electric dipole E is equal to 2P divided by 4 pi epsilon naught R cube. At this point, resultant electric field direction due to electric dipole acts away from the plus Q charge. So, in this case, magnitude of electric field at a point on its axial line due to electric dipole E is equal to 2P divided by 4 pi epsilon naught R cube, and direction of electric dipole moment acts from minus Q charge to plus Q charge. Angle between P vector and resultant electric field at a point on its axial line due to electric dipole acts 0 degree with each other. So, in the electric field due to electric dipole at a point on its axial line, magnitude E is equal to 2P divided by 4 pi epsilon R cube. Then, resultant electric field at a point on its axial line is directly proportional to electric dipole moment to P and inversely proportional to cube of the distance of the point from the midpoint of the electric dipole. So, next topic, electric field due to an electric dipole at a point on its equatorial line. See one electric dipole, minus Q charge, plus Q charge. These two equal magnitude and dissimilar charges is separated by 2D distance. It will constitute electric dipole. Midpoint of the electric dipole O. Direction of electric dipole moment acts from minus Q charge to plus Q charge. Then we assume one point on its equatorial line. This is equatorial line. That we assume one point on its equatorial line P in our aim to determine what is the resultant electric field intensity due to dipole. So, plus Q charge produces electric field intensity at this point is away E1. This negative charge produces electric field intensity at this point is directed towards the charge E2. So, at this point, the resultant electric field intensity is directed towards like this. So, at a point on its equatorial line, electric field due to an electric dipole acts, which is parallel to the dipole axis, but acts opposite the direction of a dipole moment. At this point, the magnitude of electric field intensity E is equal to P divided by 4 pi epsilon naught R cube. So, in this case also, resultant electric field intensity at a point on its equatorial line is inversely proportional to cube of the distance of the point from the midpoint of the electric dipole. And one more case, angle between direction of dipole moment and the resultant electric field at a point on its equatorial line, angle between P vector and E vector is 180 degree, because the direction of dipole moment acts along this direction, but the resultant electric field at a point on its equatorial line acting in opposite direction, both P vector and E vector is angle 180 degree with each other. Then next, one more topic, electric dipole in a uniform electric field. Electric dipole in a uniform electric field. Let me consider uniform electric field intensity directed towards the right. Let me assume an electric dipole is subjected within uniform electric field. Minus Q charge and the plus Q charge is separated by 2D distance. It will constitute electric dipole. Direction of dipole moment acting along this direction. So, now the dipole axis makes the theta angle with the direction of electric field. So plus Q charge experiences electric force along the direction of electric field QE, minus Q charge experiences electric force in opposite in the direction of electric field F is equal to minus QE. Then both equal magnitude of charge act in opposite direction, but the line of action do not coincide, resulting torque is experienced by electric dipole subjected within uniform electric field, but the direction of dipole moment P makes the theta angle with the direction of electric field experiences torque. Tau is equal to P sin theta. In vector notation, tau vector is equal to P vector cross E vector. Here theta is the angle between direction of dipole moment and the direction of electric field intensity. P is the electric dipole moment. E is the uniform electric field intensity. Torque experienced by an electric dipole subjected with a uniform electric field. So in vector notation, tau vector is equal to P vector and E vector. So direction of torque is a perpendicular to the plane containing P vector and E vector. So next topic. Electric potential energy of dipole in a uniform electric field. Let us consider uniform electric field directed towards the right. Let me assume an electric dipole minus Q charge and plus Q charge separated by a 2D distance. It will constitute electric dipole. Direction of dipole moment acts along this direction from minus Q charge to plus Q charge. Thus the dipole axis makes the theta angle with this direction of electric field. At this condition, it possesses a potential energy U is equal to minus Pe cos theta. So this is the expression to represent potential energy of the electric dipole subjected within uniform electric field at the position of angle theta. U is equal to minus Pe cos theta. In vector notation, U is equal to minus P vector dot E vector. So next topic in electrostatics lesson, electric field at a point due to a point charge. Let us consider one point charge is placed at a point O in air medium or vacuum or free space. It will produce electric field around it. In an electric field, let me assume one point to P. In our aim to determine the electric field at a point P due to a point charge. Distance of the point P from the point charge is R. So electric field at this point P due to a point charge E is equal to Q divided by 4 pi epsilon naught R square. Then electric field at a point P due to a point charge is in R medium or vacuum or free space is directly proportional to magnitude of charge and inversely proportional to square of the distance of the point from the point charge. Then electric field intensity at a point P due to a point charge not only depends upon the magnitude of charge and the distance of the point from the point charge, and also it depends upon the medium also. This entire system is situated within a medium of relative permittivity epsilon or medium of permittivity epsilon. At that same point, electric field intensity at a point in a medium Q divided by 4 pi epsilon R square. Here epsilon is equal to epsilon naught electric field at a point inside the medium Q divided by 4 pi epsilon naught R square. So Em, which is equal to Q divided by 4 pi epsilon naught R square, is electric field at a point due to a point charge in R medium divided by epsilon naught. So inside the medium, that point charge produces electric field at this point is decreases epsilon r times. So next topic, electric potential. So electric charge not only produces electric field around it, it will produce electric potential also. Let us consider one point charge is situated in air medium at a point O. It will produce electric field and also electric potential. Let me assume one point to P in an electric field produced by the point charge. Distance of the point P from the point charge R. In our aim to determine the electric potential at a point P due to a point charge, V is equal to Q divided by 4 pi epsilon naught R. So electric potential at a point P due to a point charge is directly proportional to magnitude of charge and inversely proportional to distance of the point P from the point charge Q. Then electric potential produced by the point charge near it not only depends upon the magnitude of charge and the distance of the point from the point charge and also depends upon the medium. So the entire system is without disturbing is subjected within the medium of relative permittivity epsilon r and the medium of permittivity epsilon, then produces electric potential at this point. Vm is equal to Q divided by 4 pi epsilon r. So Vm is equal to Q divided by 4 pi epsilon naught r. So Vm, which is equal to Q divided by 4 pi epsilon naught into r, is electric potential produced by the point charge at this point in r medium divided by epsilon r. So inside the medium, this point charge produces electric potential is decreases epsilon r times. Next topic, relation connecting in between electric field intensity and electric potential. Let us consider one point charge Q is placed at this point O in vacuum. Let me assume 2 points A point and B point in an electric field produced by the point charge Q. Distance between the 2 points is dx. This positive point charge produces electric field is direction away from the positive charge. Suppose if it is negative point charge produces electric field intensity at this point is directed towards the negative charge, but in the case of positive point charge, direction of electric field is away from the positive charge. So let me assume 2 points in an electric field, A point and B point. The distance between the 2 points is dx. Let me assume one unit positive charge, test charge Q0. So calculate the amount of work done in moving a unit positive charge from B point to A point. Work has to be done by the external source against the electrostatic repulsive force. This is the positive unit positive charge is moved from B point to A point. Actually this point charge, positive point charge, this positive unit test charge, both is positive charge. This test charge experiences repulsive force. In order to overcoming the repulsive force, the test charge, unit test charge is moving from B point to A point. Work has to be done on the charge. That work done is nothing but potential difference between 2 points, A point and B point is minus E dot dx. So potential difference between the 2 points in an electric field produced by the source point charge. Total amount of work done in moving a unit positive charge from one point to another point against the electrostatic repulsive force. The difference in potential is nothing but amount of work done. V is equal to minus E dot dx. Then electric field intensity E is equal to minus dV divided by dx. So electric field intensity is also defined as negative gradient of potential, is also called electric field intensity. Then electric potential at a point due to an electric dipole. Let us consider one dipole, minus q charge and plus q charge, to equal magnitude and dissimilar charges separated by a 2d distance. It will constitute electric dipole. Midpoint of the electric dipole O. Let me assume one point P. So in our aim to determine the electric potential at a point P due to an electric dipole, R is the distance of the point P from the midpoint of the electric dipole. Theta is the angle between PO line and the axis of electric dipole. Electric potential at this point P due to an electric dipole, V is equal to P cos theta divided by 4 pi epsilon naught R square. So electric potential at a point P due to an electric dipole, V is inversely proportional to square of the distance of the point from the midpoint of the electric dipole. So next topic, electric flux. Let us consider one closed surface. Area of the surface area A. In this region, electric field acts along this direction. So normal drawn to the surface n cap or A vector. At this point, direction of electric field acting along this direction. So electric field and the normal drawn to the surface makes the theta angle with each other. So what is the electric field, electric flux through the closed surface? Pi, which is equal to E A cos theta. Electric flux is a scalar quantity. Magnitude of electric flux can be calculated by using this equation. Pi is equal to E A cos theta. E is the magnitude of electric field intensity. A is the surface area. Theta is the angle between normal drawn to the surface and the direction of electric field. So electric flux is defined as total number of electric lines of force crossing through a closed surface is called electric flux. Electric flux is a scalar quantity. SI unit of electric flux, electric field intensity, Newton divided by Coulomb, and the surface area meter square. So therefore Newton Coulomb inverse meter square is the SI unit of electric flux. Then Gauss law. Let us consider one point charge, positive point charge Q. This positive point charge Q is encloses with the closed surface S. This positive point charge produces electric lines of force is away. This is the electric lines of force produced by the positive point charge. This is one closed surface. So therefore, Gauss's law gives the information to us. Magnitude of electric flux originating from the point charge encloses with the closed surface S. So electric flux produced by the electric field pi is equal to 1 divided by epsilon times net charge enclosed by the closed surface. It is the Gauss's law. So Gauss's law states that total flux produced by flows through the closed surface, which is equal to 1 divided by epsilon times net charge enclosed by the closed surface. So electric flux flows through the closed surface or originating through the closed surface is entirely depends upon magnitude of charge enclosed within the closed surface, which is independent of location of the charges inside the closed surface. So very important expression. Gauss's law, pi is equal to Q divided by epsilon naught. Then applications of Gauss's law. So one of the application, electric field due to uniformly charged wire. Let us consider infinitely uniformly charged wire. Then it possesses a positive charge. Infinite length of wire giving the positive charges are uniformly distributed along it lengthwise. So lambda is the linear charge density. Linear charge density is defined as charge per unit length of the wire. SI unit of linear charge density, Coulomb per meter or Coulomb meter inverse. So let me assume one point to P from the light straight charged wire. Distance of the point to P from the wire is R. Electric field at this point P produced by the uniformly infinitely charged wire E, which is equal to lambda divided by 2 pi epsilon naught R. Electric field produced by the uniformly charged wire at this point is directly proportional to linear charge density, is inversely proportional to distance of the point P from the uniformly charged wire. So not only depends upon the linear charge density and the distance of the point from the charged wire, and also depends upon the medium. So this entire system is situated within the medium of relative permittivity and the medium of permittivity. Electric field at this point inside the medium, which is equal to lambda divided by 2 pi epsilon r. So Em is equal to lambda divided by 2 pi epsilon r r. So the Em, which is equal to lambda divided by 2 pi epsilon r is E divided by epsilon r. So this entire system is situated inside the medium. Electric field at this P point is decreases epsilon r times. Then electric field due to uniformly charged plate sheet. Let us consider one charged plate sheet. That plane sheet, its surface it possesses a positive charge. That entire positive charges are uniformly distributed on its surface. It possesses a surface charge density plus sigma. Surface charge density sigma is defined as charge per unit surface area, SI unit, coulomb per meter square or coulomb meter power minus 2. Let me assume one point, one side of the uniformly charged plane sheet. Electric field at this point P due to uniformly charged plane sheet E is equal to sigma divided by 2 epsilon r. Not only at this point P, in other side also electric field at this point due to uniformly charged plane sheet, magnitude E is equal to sigma divided by 2 epsilon r. Here sigma is the surface charge density, epsilon r is the permittivity of free space. At this P point, magnitude of electric field produced by the infinitely charged plane sheet E is equal to sigma divided by 2 epsilon r. But the direction of electric field at this point due to infinitely charged plane sheet is away. Due to positive charges is accumulated on its surface. So next topic, one of the applications of Gauss law, electric field due to uniformly charged spherical shell. Let us consider conducting charged spherical shell. Center of the shell O, radius of the shell R. Let me assume positive charge Q. That positive charge Q is given to the spherical shell. That entire positive charges are uniformly distributed on its surface. Let me assume one point inside the shell P. Distance of the point P from the center of the uniformly charged hollow spherical shell, that point is R. In our aim to determine the electric field at this point P inside the uniformly charged spherical shell, E, which is equal to 0. Not only at this point, you take at any point inside the uniformly charged spherical shell, electric field is 0 due to electric field is a vector quantity. At any point inside the uniformly charged spherical shell, resultant electric field get cancelled with each other. At any point inside the uniformly charged spherical shell, E is equal to 0. Let me assume one point P on its surface of the uniformly charged spherical shell. Distance of the point P on its surface of the spherical shell from the center of the shell is R. Here R is equal to capital R, which is equal to radius of the uniformly charged spherical shell. Electric field intensity at this point on its surface E, which is equal to Q divided by 4 pi epsilon naught, actually R square. Here R is equal to radius of the spherical shell. Then electric field intensity at this point on its surface of the uniformly charged spherical shell, Q divided by 4 pi epsilon naught, capital R square. Then we assume one point at the outside the uniformly charged spherical shell P. Distance of the point P from the center of the uniformly charged spherical shell is R. What is electric field intensity at this point P due to uniformly charged spherical shell? E is equal to Q divided by 4 pi epsilon naught small r square. So, in this case, electric field due to uniformly charged hollow spherical shell at the center, not only center, at any point inside the uniformly charged spherical shell, electric field intensity is 0. At the point chosen on its surface of the uniformly charged spherical shell, electric field intensity, that is the maximum electric field intensity, E is equal to Q divided by 4 pi epsilon naught r square. We assume the point outside the uniformly charged spherical shell, the distance of the point increases from the surface of the uniformly charged spherical shell, then electric field produced by the uniformly charged spherical shell goes on decreases because E is inversely proportional to square of the distance of the point P from the center of the uniformly charged spherical shell. Then next we are going to see about electric potential due to uniformly charged spherical shell. Electric potential is a scalar quantity. Electric potential due to uniformly charged spherical shell at its center electric potential at its center of the uniformly charged spherical shell V is equal to Q divided by 4 pi epsilon naught r. Not only center, it shows at any point inside the uniformly charged spherical shell, electric potential V is equal to Q divided by 4 pi epsilon naught r. Then electric potential at this point on the uniformly charged spherical shell also V is equal to Q divided by 4 pi epsilon naught r. Let me assume one charged spherical shell that the entire charges are uniformly distributed on its surface. Then electric potential at its center or at any point inside the uniformly charged spherical shell or at any point on its surface of the uniformly charged spherical shell, potential of the uniformly charged spherical shell V is equal to Q divided by 4 pi epsilon naught r. But the electric field intensity at any point inside the uniformly charged spherical shell is 0. On its surface, electric field intensity is maximum. E is equal to Q divided by 4 pi epsilon naught r square. We assume the point outside the uniformly charged spherical shell, electric field intensity E is equal to Q divided by 4 pi epsilon naught r square. So the distance is increases from its center outside the uniformly charged spherical shell. Electric field intensity is produced by the uniformly charged spherical shell goes on decreases. But one more case here, surface of the uniformly charged spherical shell and electric field lines produced by the positive charge is at any point is right angles to each other. Not only at this point, we assume surface of the uniformly charged spherical shell and the electric field lines produced by the positive charge is always right angles to each other. So electric field lines produced by the positive charge is always right angles to the surface. Due to the positive charge, electric field lines is directed away from the positive charge. Next topic, sharing of charges between the two charged bodies. Let us consider two spherical shell. One spherical shell, radius of the spherical shell R1. Another spherical shell, radius of the spherical shell is R2. Let me assume charge given to the first spherical shell is Q1. Charge given to the second spherical shell, hollow spherical shell is Q2. Surface charge density of first spherical shell is sigma 1. Surface charge density of second spherical shell is sigma 2. Potential of the first spherical shell V1 is equal to Q1 divided by 4 pi epsilon naught R1. Potential of the second uniformly charged spherical shell V2 is equal to Q2 divided by 4 pi epsilon naught R2. Electric field intensity on its surface of the uniformly charged first spherical shell E1 is equal to Q1 divided by 4 pi epsilon naught R1 square. Electric field intensity on its surface of the uniformly charged spherical shell E2 is equal to Q2 divided by 4 pi epsilon naught R2 square. Now, Both the uniformly charged spherical shell is connected by a thin conducting wire. Positive charge is flows from higher potential to lower potential, but negative charges flows from lower potential to higher potential region. So, due to redistribution of charges takes place till both the spherical shell attains a same potential. After distribution, both the sphere possess a same potential. V1 is equal to V2. After sharing of charges or after redistribution of charges, both the spherical shell attains the same potential. So Q1 divided by 4 pi epsilon naught R1, which is equal to Q2 divided by 4 pi epsilon naught R2, 4 pi epsilon naught, 4 pi epsilon naught. Then Q1 divided by R1, which is equal to Q2 divided by R2. Then after distribution of charges, both the spherical shell attains the same potential. Then the ratio of charges on the two spherical shell Q1 divided by Q2 is equal to R1 divided by R2. After redistribution, the ratio of potential of both the spherical shell V1, which is equal to V2, both the potential is same, then ratio is 1:1. Then what is the ratio of surface charge density of both the sphere? Already we know that in redistribution of charges, Q1 divided by Q2, which is equal to R1 divided by R2. Then we know that another expression, surface charge density sigma is equal to charge per unit surface area. Then charge on the spherical shell Q is equal to sigma A. So charge on the first spherical shell Q1, which is equal to surface charge density of first spherical shell sigma 1, then surface area of the first spherical shell A1, then Q1 is equal to sigma 1, surface area of the spherical shell 4 pi R1 square. Then charge on the second spherical shell Q2 is equal to sigma 2 4 pi R2 square. Substitute in this equation Q1 divided by Q2, which is equal to R1 divided by R2. Q1 value sigma 1 into 4 pi R1 square divided by sigma 2 into 4 by R2 square, which is equal to R1 divided by R2. So 4 pi get cancelled, R1, R1, R2, R2. Then sigma 1 divided by sigma 2, which is equal to sigma 1 divided by sigma 2 into R1 divided by R2, which is equal to 1. Then sigma 1 divided by sigma 2, which is equal to 1 divided by R1 divided by R2. Then sigma 1 divided by sigma 2, which is equal to R2 divided by R1. So in the redistribution of charges, surface charge density are in the ratio which is equal to R2 divided by R1. Then after redistribution, what is the electric field intensity on its surface of the both the spherical shell ratio? E is equal to electric potential divided by distance. Here, electric field intensity on its surface E is proportional to first spherical shell potential, both the sphere potential remains same V divided by radius of the first spherical shell is nothing but distance R1, equation number 1. Then electric field intensity on its surface of the second spherical shell E2, after sharing of charges, potential of the second spherical shell also V divided by distance is nothing but radius of the second spherical shell R2, equation number 2. So what is the ratio of electric field intensity on its two spherical surface? E1 divided by E2, which is equal to V divided by R1 into R2 divided by V. It cancel. Ratio of electric field intensity on its surface of the two spherical shell R2 divided by R1 after redistribution of charges.